Okay, so in the video clip, we had reviewed the data types, the Titanic Tree dataset, and you might recall so this is a Python notebook in Google Colab. We initially had taken in our data through an R package, so we installed Activate R Magic. That allowed us to then apply R commands. We had installed tidyverse R, which allowed us to do some more sophisticated data manipulation. And it was this package, package PASWR, which we had installed and we made available in the library. And this is what gives us our Titanic Tree data. Using Titanic verse R, we looked at our data using the glimpse, a verb from tidyverse, and we were able to see we had 1,309 passengers, 14 columns. We had done some basic pivot tabling. We installed rpart from R, and we had installed rpart plot for plotting, and then using fairly simple construction in terms of attributes, just looking at p-class and age, we predicted the outcomes in terms of people's survival aboard the Titanic. Also, we then went on to estimate a C tree by installing initially the party package. So we installed party into R and then performed the C tree modeling. That doesn't visualize so well in Google Colab. So we went into the native RStudio desktop app, and we set up the same code and visualized the C tree. And from fairly, again, basic type attributes, we're not using the 14, just 4 here. So the sex, p-class, sibling, spouse, and age. We set out a C tree. Now this is based on Hal Varian's paper in 2014, New Tricks for Econometrics from the Journal of Economic Perspectives. And basically, we can see fairly clearly if you're male, if you're second and third class, if you're older than 9, your survival prospects not very good at all. If you're male, second, third class, older than 9, so younger than 9 but big family, so sibling, spouse greater than 2, survival prospects weren't that good. If you're female, first and second class, your survival prospects were really good. Okay, so that's a useful visualization, and it helps us to understand a little bit in a very visual way but very impactful way how survival was influenced by the passenger attributes. Now we then proceeded to go into read in the same data into a Python notebook. So we wrote out that Titanic Tree data set. We called it Titanic3.csv. That goes then into the content folder, which you can see here. And then we read that back in using Panda library. So we installed the Panda library and then read the same data back into this Python notebook in the same Google Colab. We imported in more libraries, and then we performed some basic analysis, and we had got as far as setting out again the variables and converting the Titanic. So basically we had changed female and male, Southampton, Cherbourg, Queenstown, using in code library available in sklearn, and they then got converted to female became 0, male became 1, Southampton became 2, Cherbourg became 0, Queenstown became 1. Now, in the analysis that we're going to perform below, we'll basically just go back to what was in the original C tree proposed by Hal Varian, and that was P-class, sex, age, and sib and SS, so sibling and spouse. Okay, so we dropped from the Titanic data set this detail, including embarked, and then we reorganized the Titanic Tree data set. So even though originally it looked like this, it had this type of ordering, we were able to set survived to become the first column, and then we had P-class, sex, age, and sibling, simply by using this command here. Titanic Tree is now equal Titanic Tree survived, then P-class, then sex, then age, then sibling or spouse. Now this is the same data that was used by Hal Varian. We removed also, we dropped the variables or the rows here that where there's missing values. Okay, so one of the in terms of changing the shape, in the original passenger list we had 1,309. We dropped where embarked and age variables were missing. Now we didn't have to drop embarked, but I did. But there's only 2, I think, in that, so it's not it's innocent enough. But there was quite a few ages missing, right? When we reviewed our data set, one of the very evident things that emerged was the number of ages that was missing, right? And that's 263, if I recall. So we removed those rows from our data, and then we then had to set out, okay, look, this is our data set. It's now down to 104,044 passengers, and we have 5 variables. So the 5 are survived, P-class, sex, age, and sibling or spouse. Now what we're going to do with these is to run them in a variety of different through a variety of different machine learning techniques, and we're going to model them so that we can predict, like what we had done before, the outcome. Now, in addition to this, which we didn't do before with the Hal Varian data and the techniques applied in the Hal Varian paper, we're going to split into test and train. Okay, so our data set, basically the new Titanic Tree data set, after pruning back the missing values, we have P-class, and we have survived, sex, age, sibling, spouse, 1,044 rows by 5 columns. Now we want to split apart, separate out, if you like, the P-class and treat that, sorry, the survived, and then predict survived using the other variables, right? So if we okay, so let's run this one more time, and you can see now we've put survived here. So previously survived was the second column, and now we've put that to be the first column because we've ordered the variables in this fashion here, right? So our Titanic tree appears like this, and then using iLog, if we want to just view what iLog, how do we separate survived from the other variables, we can use Titanic tree iLog, and we have row columns, so we're taking column 1, and then to get the other columns going 1 to 5. So if you like, in the original data set, 0, 1, 2, 3, 4, but up to 5, then when we go 1 up to 5, so 0, 1, 2, 3, 4, up to 5, we're capturing these 4 columns here. So this when we apply Titanic Tree ilog 1 to 5, we're taking columns 1 to 5 or up to 5. Okay, so we have these 4 columns here. Now, why is that? Why are we going through that? Just to explain the process we go through to split, first of all, our data set into the independent and the dependent variable, right? So we create X, which is this array here that includes P class, sex, age, and sibling, again, following the C3 visualization from Hal Varian. And then Y is the variable that we want to predict, right? We want to predict survival. So that's the first column in the data set, so survived. Okay, so we've split apart those two, the X's from the Y's. Now we've got to split the data into training and the testing. And that's important because it may be straightforward to get a reasonable fit in sample, but when we go out of sample, is our model robust? And machine learning that's available, there's a whole plethora of machine learning available in sklearn, but the test of robustness is, do our models predict well out of sample, right? In sample, they may predict well, we would like that at a minimum, but also out of sample, they should perform well. So we split our data up using sklearn. And we have in our data set now, we have X train, X test, Y train, and Y test. So 20% of our data goes into the testing data and 80% goes into the training, which is where we initially estimate the model, right? Okay, so we apply those. And we've set a seed, so that will be the same in each instance. Then we standardize the variables. That can be important sometimes because you don't want one variable hogging all the explanatory power, so you tend to standardize. And that sometimes can lead to each column then having a similar mean standard deviation. Okay, so we then apply a battery of machine learning models. And again, we're invoking sklearn, so we're using logistic regression because we're predicting a 0, 1, and we're using the data that we're using is the training data is the X train and Y train. So it's 80% of our data set. Logistic regression, KNeighbors classifier, support vector machine, a second support vector machine is used here. A Gaussian NB naive Bayes technique. We're using decision tree classifier, random forest classifier, and then estimating model accuracy. Okay, so we run these models and that is executed reasonably fast. And then we get the model accuracy for each model that we had set up and run. And the in sample or the training accuracy can be quite high. And a number of the models on the decision tree classifier, we're getting 89%. Also on the random forest, we're not sure if that's coming from overfitting, but it looks very promising. 77%, 80%, 77% for support vector machine, linear classifier, KNeighborsNeighbor 82, and then logistic regression 79. So that's in sample. Of course, we want to see that for out of sample, and I mean, we want to see take the coefficients and the parameters that are estimated and using the models that we estimated in the training, apply those on the test data set. That's the 20% that was excluded from the original model estimation, and see how well our models perform. And we will use confusion matrices in order to adjudicate in terms of model accuracy. And interestingly enough, there is quite a significant change here. These two models, which were such strong performing models, the decision tree and the random forest, their performance falls off quite a bit. Otherwise, it's 78, 80%, which is the second model here is the KNeighborsClassifier training, looks quite good. 78, 79, so very close to 80. 76, okay, and 77. Now, to understand a little bit the confusion matrix, it's worth just looking at what's entailed here. So perhaps we can put this up against the actual model outputs. Okay, so what we've done here is we've estimated the confusion matrix for each of the machine learning models. And in the confusion matrix, we have, if you like, predicted and actual. So we were trying to predict the degree to which individuals survive. So that would be a true positive. And again, if I just go a little bit lower to explain, if we take, for instance, the y-test data set, that was made up of, we can see here, there were 90 individuals in the sample who survived. So the ones here denote survived, 0 denote drowned. And then overall, the number of observations here in the test data set was 209. So 90 out of the 209 survived. That meant that 119 perished or drowned. Okay, so in our what we're looking for then are true positives. We're looking to get as close as possible to the 90 in terms of true positives. And then for the survived, we're looking for, so 90 for the true positives, and then 119 for the true negatives. Now, none of these do we get 119 or 90, right? But that would be the sweet point, getting 119 and 90, 119 and 90, so we fall short. Okay, the question is then, how do we fall short in terms of the model accuracy? Well, we predicted, to understand the confusion matrix, 90 survived, but in terms of when we predict in the first model, which is using the logistic regression training, right, it predicts 59, right? So it's a true positive. So it said we predicted that 59 would survive. Who actually survived? And then predicted negative, we predicted using the logistic regression model, we predicted that 104 drowned who actually drowned. And then we predicted that 15 survived but actually drowned. And we predicted 31 using the logistic regression model. We predicted that 31 drowned but actually survived. So when you add the 31 and the 59, we get 90. When you add 104 and 15, we get 119. Okay, so turns out it's not a bad model, all in all, 78%. The best model, of course, is the KNeighborsNeighbor training accuracy, 82% accuracy with the training data, but has 80% accuracy with the test data. And that's kind of sort of a litmus test here. That's the one to beat.